Okay, so in this video we are going to solve the area bound by the curve of a function and the x-axis. We see that this is the shaded region representing that area. And we're going to solve this using an infinite number of rectangles. We're going to use RRAM as the number of rectangles approaches infinity. And we see that our left bound here is from -3 to the right bound, which is +3. And here is our function f of x. So as usual, we start by calculating delta x, which is b minus a over n. Our a value is the left side of our interval. Our b value is the right side. So this is 3 minus -3 over n, which becomes 6 over n. And we leave this as n because infinity is not a number we can plug in for n. So we will have to introduce limits to evaluate this. After delta x, we want to find the generating function for the x coordinates. We call that the x sub I function. And for RRAM, x sub I is defined as a plus I times delta x. So our x sub I will be -3 plus 6i over n. And I will just rearrange that to be 6i over n minus 3. I like to keep my minus signs in between two terms. And now we have to plug that x sub I into our function f of x. So now we have f of x sub I, which is 1/8, times, we're going to replace the x variable with 6i over n minus 3, close the parentheses. Since x is squared, we're going to square this, and then we have the plus 3 that follows. Now we would like to FOIL this. And next I'm going to distribute this 1/8 through here. And since these are both constants, let's combine them. And that is our function f of x sub I. Now, we want to plug this into our area formula. Our area formula is going to be modified slightly because it's going to have a limit as the number of rectangles goes to infinity. And then we have delta x times the sum of f of x sub i's from I equals 1 to n. Just so that we can recall, the delta x is the width of each rectangle, and the sum of f of x sub i's is the sum of the heights, and the width times height is the area of each rectangle, and then the sum gives us the total area. So now we would like to substitute our delta x and our f of x sub I into here. And now we would like to isolate the I terms in the summations so that we could apply the summation formulas. So we have the area is equal to the limit as n goes to infinity. 6 over n is my delta x. I'm going to put a parenthesis here because I'm going to separate this summation into 3 summations, one for each term. I want to get I squared by itself in the summation, so the 9 over 2n squared I will pull out as a constant times the summation of I squared. And then for the next term, I'm going to take the minus 9 over 2n as my coefficient times the summation of just the I. And then this one has no I terms, it's just a constant, so we can just put that inside and use the constant rule for summations. Now the I squared I'm going to replace with its summation formula. So that is n times n plus 1 times 2n plus 1 over 6. The I is replaced by n times n plus 1 over 2. And I forgot to write my I from 1 to n on each of these. And the constant just gets multiplied by n. Now we're ready to simplify this. As I distribute this 6 over n through here, this is going to become, well, first thing is I don't really need to FOIL all of this. When we do limits to infinity, we are only concerned with the highest exponent term in the numerator and the denominator, and we can evaluate the limits using rules that apply to rational functions. So the highest exponent term with its lead coefficient from the numerator is going to be 2n times n, so that's 2n cubed. 2n cubed times 9 is 18n cubed times the 6. And then the denominator will have n times n squared, so that's n cubed times the 2 and the 6, and that would give us 12n cubed in the denominator. If we simplify all of that, we get 9n cubed over n cubed. I have a minus here, so when I distribute this to the next term, I'm going to have a minus. And when I multiply 6 over n with all of the terms we see here, again, we're only interested in the highest exponent term with the lead coefficients. So that gives me n times n is n squared times 9 times the 6 from out here. So that's 54n squared. The denominator would be 2 times 2n, which is 4n, times the n from outside, that's 4n squared. And then we can simplify this and we get 27n squared over 2n squared. And then the last term would become 99n over 4n. So you can do that algebra yourself. It's just distributive property and simplifying. And once we have this, we see that because the top term and the bottom term have equal exponents, the limit would be the ratio of the coefficients. So this first term, the limit as n goes to infinity would be 9. This second term, the limit as n goes to infinity would be minus 13.5. And this last term, the limit as n goes to infinity would be positive 24.75. And if you add all of these numbers up, you get 20.25. That is the exact area, and that is the end of the problem.